I want to review from yesterday a little bit and then kind of tell you what I'd like you to try to do this weekend anyway. Okay, so yesterday, that's how it's coming away. Yesterday we were looking at the field comparison worksheet, and on page 3, just to remind you, what we did was we said that um, because these fields are uniform, the G field and electric field are uniform, and thinking about the G field, noticing how it's always here on Earth anyway, it's 9.8 or 10 meters per 10 meters per second each second, or also 10 kilograms, 10 newtons per kilogram. It's constant. So noticing it's parallel and uniform, maybe it's the same is true for the E field. We haven't proven it or anything, but that's kind of our supposition at this point. So the G field would be constant no relationship, and the E field would be constant no relationship for an infinite plane of mass. Then the next thing we looked at was a point mass, and we found out that it follows an inverse square relationship. That's what we found out kind of in lab for the for the electric force. And we compared that to the gravitational force, and it's also an inverse square relationship. And we found out that the gravitational field was proportional to g times the mass, the central mass, divided by the inverse, or excuse me, the inverse multiplied by the inverse square of the distance. We could do the same thing for the electrostatic force. We could say it's equal to kq1, q2 over r squared, or we could say the electrostatic force is equal to q, the charge that's out here somewhere, some test charge, times whatever E field exists out there. This is a very important equation that kind of helps you on the PhET simulation for E fields. And we found out that the E field is also inversely proportional to the square of the distance. And so here we have the two relationships. This one was kind of one that should have been pretty easy for us. Then we started thinking about an infinite line of mass or infinite line of charge, which is really, that's kind of peculiar. You know, where does that come about at? Well, what I want you to think about for this is, especially kind of skip over the line of mass because that's kind of difficult. The line of charge, though, imagine that we have this line of charge sitting here, and we're trying to figure out the E field at some distance. It could be any distance along here. And again, it doesn't have to be right in the middle. Remember, this is infinitely long, so it could be anywhere in here. But if I look at the E field, there's going to be kind of a pull this direction. There's going to be a pull this direction toward this negative charge. And the X components, the parallel components to the line of charge, they cancel. But the vertical components don't. So while it's true that that force gets less as you get further and further away, it doesn't get less like the point charge does, because these two vertical components here and here kind of reinforce one another. And so again, our supposition is that while it gets less, it doesn't get less as fast as the inverse square. And so we just kind of guess that it might be just simply an inverse relationship. Okay, so that's what we looked at. And we haven't proven anything though, and we need to start thinking about a lab that we can do. And so now I kind of want to throw it out to you guys and hear what you guys think of, can you think of any other phenomena that exhibits an inverse square relationship? Um, we obviously can't do electric fields because I don't have an electric field measurer in class. Um, if we were to spray paint at different distances from the paint gun, that would be an inverse square, but we don't really have anything that's too messy. Can you think of any other phenomena, though, that might be an inverse square? Something that we can measure in class. I mean, it's not going to be electrostatic force, but it will be an inverse square, so therefore we can use it as a model. Can you guys hear me? I'm starting to get a little bit worried that you guys can't hear me or respond. Is it cutting out on you? Oh, okay. You're just thinking about it. Okay. A little kind of a tough question. Okay. Let me think about, um, let me see if I can help you a little bit. When we're talking about an inverse square, I want you to think about why it's decreasing as you move further and further away. As you move further and further away, try to imagine this big sphere at which it could be spread apart. You know, it's kind of like spreading the same amount of energy. It's not really energy, but it's spreading whatever influence that is over a very larger and larger area. That's why it kind of follows this inverse square relationship, because as you go further and further away, that area, which is a square thing, gets bigger and bigger. Yeah, how about a light? So in other words, if you had shine a flashlight on, if that flashlight is really close to the wall, it's going to be really bright. But if you move twice as far away, now the spot on the wall is only going to be one-fourth as bright because it's spreading over a much larger area. You have to kind of spread that over a much bigger area. So yesterday I was getting some funny looks of, well, wait a second. I don't know if that's an inverse relationship. I don't know that's really, I don't know that's constant. And I said, okay, we need to do a lab. We're going to use light as our model to do this lab. So that's kind of what I want to describe next. I want to describe the lab. And you can actually look at this lab yourself. You can download it and read it. In fact, I would like you to do that this weekend. It's on the snow day homework. Um, but let me kind of show it to you. Um, it's to graphically and mathematically model a relationship between an E field and a light source. So we're actually using a light source. It's not going to be the E field, but it will be an inverse square for a small point source, and the radial distance from the source. So what we're going to use is we're going to use a light probe. That's something we have in class that we can, take some data with. And we're going to, the computers that are in my room, we're going to use them as a light source because it's nice and flat. We're going to put a PowerPoint screen up that's white, and we're going to block it all out with construction paper except for one little dot, and that's going to be our point source. And we're going to back off the probe and see what the mathematical model is for it. Now we should already know what the mathematical model is for a point source. Okay, so that's going to be our control in a way to see if it's true or not. Then what we're going to do is we're going to cut the construction paper so that we have a diagonal line across the let's see if I have a picture down here. I don't have a picture. So we have a diagonal line across the screen, and it's going to have a white light shining through it. And so we're going to go in the middle of the screen and back up away from that diagonal line and see what the mathematical model is. And the last one's the easiest one. We're just going to take the construction paper off, and we're going to see, after taking the construction paper off, how, what the mathematical model is when you back up from the center. Okay, so that's what we're going to do the next time we get together, whenever that is. So I guess something you could do in between is read through this. I've kind of explained it to you real quick. You need to make kind of a spreadsheet on your computer so you can record the data. But other than that, there's not much more you need to do for that lab until we can do it. The other things that you can do, and I'm almost done. I'm going to get done a lot quicker than I thought. Is trying to save some time here. Is after we get done looking at electric fields, then we're going to look at these things called equipotential surfaces. And so what I'd like you to attempt to do, this is also on that snow day homework, is I would like you to try to work on some of these where it says equipotential surfaces worksheet. Again, I think most of these will be pretty easy. I'll give you a hint. Think about potential energy. Okay, so I think this should be pretty easy, except for maybe the equation number 8. And I think all the way to page 2, all the way through the equations, so all except for number 14. Although I think you can probably do 18 and 14 given my hints. Okay, so I'd like you to try that. That way we can whiteboard it. That'll save us some time. I don't expect you to do page 3 or anything like that. Okay, And then the other thing I'd like you to work on this weekend is another PhET simulation. Again, this is the homework, and it's dealing with these equipotential surfaces and how it's related to work. So I'd like you to follow through those instructions and do this simulation here. This is actually finding a mathematical model for the equipotential surface. Um, so kind of it's really important that you get that data to find that mathematical model. And you should be able to answer those pretty easily through 24. You should be able to draw the pictures, no problem. Okay, this should be a pretty easy one because there's no math on this one. Okay, so any questions from anybody? Okay, I have a question for you guys. What did you think about this one? This is join.me. What did you think about this one compared to the AnyMeeting? Which one do you like better? Okay. Oh, okay. Okay. Oh, so you had to download soft. Oh. Yes. Sorry. Sorry. Oh, I don't want you guys to have to use your phone. That might cost some money. I don't know how much that's going to cost. Maybe we need to field run some of this in class. That way we can figure out workarounds and stuff. Are you guys using your student computers or your home computer? Okay. 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 So it sounded to me like the majority said that any meeting was better than this. A few people said it didn't really matter, and then a couple, I think, said that they liked this one better. All right. Okay. All right. I really appreciate your time. I guess it only took about 12 minutes. I'm going to post this video just in case anybody didn't make it to the meeting. Thanks again, and see you guys later.